Alright, so the YouTube is recording right now, and Discord is live streaming. So I think we are ready to go. Are there any questions from last time? Good evening, Nick. Any questions from the last lecture? No questions? Okay. Well, the test was a little bit time consuming, I would say. The idea is this is a fully online test and all the tools are available. Um, and I just wanted to kind of make it a fair test. Um, Basically, if once I grade it, I know the distribution, and I'll be maintaining the same usual distribution of A, B, C, D, F. So, if the best score is 80%, then I will, use, you know, one of many different methods to rescale the thing. All right, so it is 5:30. I am getting started with the lecture. So in case you haven't noticed, the test has the key to the exam is already posted on YouTube. They're in exam 2. So if you go to exam 2, which is the text channel exam 2, and you go to the pinned messages, the solutions for question 1, 2, and 3, they're all recorded and posted over there. So the explanation of the answers basically add up to about an hour and a half, but that's including a lot of explanations, and so it really does not reflect how much time a person will really need in order to answer all those questions. All right, so with that out of the way, we are going to continue with what we talked about last time. So what you're seeing here in the text terminal, on the left hand side, that's C code. This is rtk.h, the real-time kernel header file. And this is intended for C programs to pound include so that we can have multi-threading. And then on the right hand side, we have the assembly code that is equivalent to the structure definitions. So this is relating back to what we have been talking about, well, I guess maybe for one lecture or so, how to implement structures in assembly code. The assembly language syntax is a little bit different compared to what we have. So in this case, instead of saying thread underscore sp colon 0, it uses a syntax called .edu. It's basically a pseudo operation that's intended only for the assembler, and it doesn't generate anything in the runtime. So this is the same thing as thread underscore sp colon 0, and the next one is equivalent to thread underscore next colon thread underscore sp2 plus in our syntax. Okay, but what I want to do is to kind of emphasize that this is what I use to write a real-time kernel. There's the assembly code. The real-time kernel itself is written entirely in assembly code. There's not a shred of C code in this. But to interface to the assembly code, there's a typical C header file. Okay, so the left-hand side is just a regular C header file with regular C prototypes. So when you look at a particular program which is entirely written in C, the way it makes use of thread is as if we are using just regular structure definitions. And then when we look at functions that make use of threads, okay, which is RTK initialize all the way up here, this line over here. So this is just a regular C call, okay, except it's not really calling a C subroutine. It is actually calling an assembly subroutine. Everything is implemented in assembly, and yet the API is C compatible. So that really is the reason why we talk about the concepts, since the last lecture, which is how to implement structures in C and C++. So are there any questions about all of this stuff from the previous lecture? No questions? Okay, all right. So if there are no questions, we're going to go back to the modules in this class. We are pretty much, almost, we're getting pretty close to the end of the entire lecture. So in terms of labs, we are done with, let's see, the previous lab that we did was a function call, and then this is the lab for today. So I'm going to release the lab right now, just so that we have some practice. And this one is about recursion. So once I release it, then we'll go ahead and start to talk about it. Today is the 21st, so 28th is going to be the due date. So it's April 28th, 5:30 p.m. So the access code is FIB because it's Fibonacci. So we'll go ahead and save and publish, and then we'll go ahead and preview. Okay, so we'll basically take a quick look at the questions. Question 1, when a function returns a scalar type, what is the mechanism in the context in this class? So where is the return value? Okay, so we should know the answer to this one already. Next. Question number 2, how are parameters passed from a caller to a subroutine? And we have already talked about this, and the previous program sort of makes use of this too. So we're going to click next. The following is the C code that you need to implement for this lab. So this is a recursive subroutine. You can see why it is recursive, because we are calling subroutine f from inside the definition of f itself. Okay. And the main function call can be assumed to be like this. We have a local variable x that we use to store the return value of calling f. So obviously the question mark is representing a value to test the algorithm. Is function f recursive? Okay, I think I just answered that question. Question number 4. First, make the code in the previous question in an actual C program so that it can be compiled and it runs, and quote unquote play with it so that you feel comfortable with the logic of the code. So that really is important, because the first thing you want to do before you implement a program in assembly, and this applies to question number 1 of exam 2 as well, is to run the C code, compile and run the C code, and then observe what it does. Okay, because if you understand how the C code works, then the implementation in assembly code is a translation process. Okay, because you already know what it is supposed to do, you just have to express the same logic in assembly code. But on the other hand, if somebody does not understand how the C code works, then it becomes almost impossible to translate the code into assembly and double check to make sure that the implementation is correct. So that really is the key, is to run the code in C first. Okay, make sure that we understand the way it works, then we go ahead and implement it in assembly. So this means, okay, if the rest of this description is then go ahead and implement in assembly, and then turn in the TTP ASM file, which is the source file. That's basically the file that contains the mnemonics. So what we want to do is to go back to question number 3, which is where the source code is. Okay, it has the source code of f, and it also has the source code of main. Your main job is to implement f, so I can give you main, so that you don't have to write the main subroutine, but which is the really easy part is main. The difficult part is, well, I shouldn't say difficult, but the main task is to implement the subroutine f. Okay, so does anyone want to compile and run this code in C first, just to observe how f is getting called when we have, let's say, n equals to 3 or something like that? Okay. We got somebody typing. Yep. Okay. So let's go ahead and do it that way. Okay. So we'll go ahead and write this code in C first. All right. Um, this also. Yeah. Go ahead. Go ahead. Oh, I thought somebody just tried. Oh, okay. All right. So we'll go ahead and implement the code in C. Just call this fib.c. It's Fibonacci. Pound include stdint.h. I'm really hoping that by now, you guys already kind of noticed that I use standard integer.h all the time because this is how I can control the width of the types. Okay, so this is using uint8 underscore t, which means the C implementation has exactly the same range limitations as your assembly code. It's kind of important to do it this way because otherwise, some code that runs in the C code is not going to run in assembly and becomes, really difficult to debug it. Um, so if n is less than 2, then we return just n itself. This pair of parentheses is not needed. It's just there so that, I can make sure that people understand which part is which part. Okay. All right. So this is how I implement the Fibonacci function, and then we have main.
Okay.
Yeah, go ahead. I thought somebody had a question. Nope. Okay. All right. So we can make this, f of, something. Obviously, we don't want to make it f of 0, 1, or 1 because when n is less than because when
Wait.
because when n is because when n is less than 2, it doesn't do any recursion. Now, if you want to test it, it's not a bad idea just to, especially when you are implementing the subroutine, it's not a bad idea.
Like drawing, like three,
Um,
two,
let's see. Okay, somebody has a hot mic and I can hear you, which means the rest of the class can hear you as well. Okay, I think that just got muted. Maybe. Okay. I can still hear myself, through the mic of one of you. Okay. I don't see it either, which is kind of interesting. Is how did it get in here? Hmm. Okay. All right. So, getting back to the question of what value we should use to test function f, you can always start with 0 or 1 because if it's hmm, is it my own mic doing it? Yeah, but I don't see anyone to ban. Hmm. Okay, so let me continue with this. So we can try f of 0 because if n is 0, the condition is going to be true because 0 is less than 2. Then we should just return 0 here. Okay. When you're implementing this in assembly, that's what you need to test first. Okay. You don't even bother with the recursive part until you have gotten the non-recursive cases implemented correctly. Okay, but since in this demonstration I do intend to demonstrate the recursive nature of the algorithm, I'm going to try f of 3 and then return 0 over here, and then we can now compile the program. Okay, And then this program can only be, you can only find out what this program is doing using GDB because it doesn't actually have any output. So we say GDB, we put a breakpoint on function f, and then we can just go ahead and run the program. So this is the first time we break, or the first time we stop in the subroutine at the entry point, and we can see that the first time we call function f, n has a value of 3. Now, when you're debugging this in assembly and you're using the trace analyzer, you can look at the content on the stack to see if the argument of 3 is pushed correctly on the stack or not. Okay, so there are many things you can find out whether your program is working or not using the trace analyzer using many different methods. Okay, so if I single step, okay, there's not much we can do with single stepping because everything is on the same line. So if I single step, you can see it is going to n equals to 2, and that's because 3 is not less than 2. And then we go to the else case in the ternary expression, and in the ternary expression, we have f of n minus 1 plus f of n minus 2. N is 3, so n minus 1 is 2. So this invocation or this breakpoint is corresponding to the invocation that is recursive from the subroutine itself. Okay. Now when n equals to 2, n is less than 2, once again, is false, which means we are going to the else part of the ternary expression. Because n is 2 in this case, n minus 1 is 1. So by calling f again here, we will have the third invocation where the value of the parameter is 1. So single step again, and that exactly as what I said. Okay. So in GDB, if you want to get an idea of how we got here, I think we talked about this already, but it doesn't hurt to kind of mention this again. So what we can do here is we can say backtrace, which is BT. So when you say BT, it shows how we got here. Now in BT, the pound number, which is the frame number, is relative to what is the current active frame. So pound 0 or frame 0 is referring to the frame that we are on at this point. The previous frame is pound 1, and the one before that is pound 2, and then the one before that is pound 3. So main is the furthest away from the current context because main is what started everything to begin with. And we can also quite clearly see the recursive nature of f in this case because we can see the first call of f. The first call of f has an argument of 3, the next one has an argument of 2, and then the current one has an argument of 1. Okay? So do we have any questions at this point, with the tracing of this code in C? Okay, no questions. Okay, so we can also set up a breakpoint on line 5 so that when I return, we'll stop again. Okay, now if we do this in C and C++, the way I write the return statement, it doesn't really give you a whole lot of chances to find out exactly what is going on. So I can give you an alternative version of this where it is easier to visualize and find out what recursive call is doing. Okay, so if I single step and then do another BT, we are still in the last frame. Okay, and then we do this again. Now we do another BT. Now this is the second call already from the same line, so we are addressing f of n minus 2 with respect to frame number 1, because in frame number 1 n is 2, 2 minus 2 is 0, and that's how we got to the current frame over here. Okay, so this is what you can do using the debugger in code blocks. If you want to use VS Code or some other IDEs, I'm pretty sure you can do exactly the same thing. It's just that I'm not a IDE type of person, so I don't use IDE very much, especially not for this type of debugging. Okay, so I'm gonna quit here, and instead I will give you an alternative form of f. Okay, so instead of combining everything into one single return statement, which makes it kind of difficult to understand what is going on, when are we returning, and so on and so forth. So instead of doing this, okay, I'm going to comment this out. So instead of doing this, I'm going to use a very long, tedious way, but it becomes much easier to see what is going on. Okay, so I'm going to have a result local variable which is initialized to 0. So I'm going to break this up as much as I possibly can. Okay, so we use a regular conditional statement instead of a ternary expression, and we say if n is less than 2. So I'm preserving the logic of the original program, except I'm just breaking up the steps as much as I possibly can. So if n is less than 2, then we say result is n. Okay, and then at the very end here, we have one single return statement that returns the value of result. In the else case, we have, in the original code, we have f of n minus 1 plus f of n minus 2. So instead of doing everything in one single expression, which makes debugging a little bit harder, we just say result is plus equal to f of n minus 1, and then we say result is plus equal to f of n minus 2. So this way we have a lot more lines in order to place the breakpoints, and it becomes easier to really figure out the flow of the program. Where is it going, then where does it go, then where does it go, and then where does it go. Okay. Obviously, you don't need a plus equal here. You can just say your result equals to, because that's the first recursive call, but the second recursive call you should use plus equal to, because we are adding the return value of the second call to the value of the first call. Okay. All right. So this is the alternative version, and let me just make sure that it does compile. Okay, so and it should give us exactly the same result when this code runs. So do we have any questions about the C code? Okay, does everybody understand the recursive implementation of Fibonacci? More or less. Okay. Now, if you want to check your code, okay, and you want to say, well, I'm not really sure about the return value. What should it return when I say f of, say, 5? Okay. So the easiest way to do it is, just go to a web browser, look up Fibonacci sequence, and the Wikipedia page, which interesting is not the first one here, but this on this side it is the Wikipedia page. Oh, okay, that's just click here, because we are not looking at images, we want to actually locate it. So you can see that f of 0 is 0, f of 1 is 1, f of 2 is also 1, f of 3 is 2, f of 4 is 3, f of 5 is 5, f of 6 is 8, and so on. Okay, so this will give you an idea of, when you try to implement this in assembly, it will give you an idea of whether your implementation is correct or not. Okay. So are there any questions up to this point about Fibonacci itself and the code that is given to you, which is over here? Okay, no questions. All right. So what I'll do is I'm going to go back to this code here. Okay. And the question now is shifting to how are you going to write this program? Okay. Are you going to write everything in assembly in one shot and then go ahead and test whether it works or not? Or are you going to write some code, test it, write some code, test it, write some code, and test it? Yep, incrementally, using very small steps is usually the best way, simply because the tools that we have can afford us to do that. Now, if you go back about 50 years or so, when COBOL is a very well, it's still an important programming language, but but these days we have a lot of alternatives. But when you go back, about 50 years, when you write the program, you're writing the program on punch cards, okay? And you can only submit a job, like maybe once a day, and then the program will be run, as a batch job overnight, and then the next day you can go collect the printout, or the output of your program. So in that case, you don't want to do incremental, programming that much, because otherwise, each step is going to take a day as a turn over time. But the tools that we have, okay, can run on any computer, and you can make changes quickly, test it, see if it works, and then if it does work, then you can move on. If it does not work, then you can debug the code. So with that luxury, writing code in an incremental fashion is really the best way to do it. Okay. So how would you write this code if you are to run it, write it in an incremental fashion? So I'm going to switch back to the really concise single line implementation. Okay. So the question now is, well, this is the code that we want. Okay. But how do we test it? How do we write the code incrementally? So the first thing we do is to say, well, I just want to see if n is less than 2. Okay. And if it is, we return a particular value. Pick something that is unlikely to happen just by random. Okay. So we'll say 42 in one case, and then we'll say pick another number that is unlikely to happen, but it has interesting special meanings. Does anyone want to contribute ideas? 42 obviously is coming from the Hitchhiker's Guide to the Galaxy, but
It's the answer to the ultimate question.
yes, I'll pick 45. Okay. All right, so 42 or 45. Okay, so obviously this is not Fibonacci. Okay, if somebody turns in a program and this is all it does, it's not going to worth much points. Okay, because the whole point of the homework assignment is, can you implement a recursive subroutine and debug the recursive subroutine? Okay, so if this is turned in, it's not going to get a whole lot of points. But from the perspective of debugging the code, finding out whether the call is okay, whether the return is okay, whether the subroutine can read the parameter and correctly, this is a whole lot easier to debug, because if it returns a value of 42 in register A, and n turns out to be actually less than or equal to less than 2, then the code it seems to be working correctly. Okay, if it returns a 45 and n is in fact greater than or equal to 2, that would seem like, well, at least that part of the logic is working. Okay, so if this is the code, what test cases should I use to test it? I would definitely include boundary cases. So that means, f of 1 is a good test case, because 1 is the last unsigned value that is still less than 2. Okay, so f of 1 should still return 42. And then the other boundary case is f of 2, because 2 is the first unsigned value that is greater than or equal to 2. It would be the first value to get a 45 return value from the subroutine. So 1 and 2 are really crucial test cases, because those are the boundary cases. Now 0 is kind of cool too, but if it works on 1, yeah, I mean, unless there's a very special mistake, 0 is going to work. Okay, and the same applies to 3, because if 2 is working, then 3 is probably going to work as well. Okay, so there are very few kinds of bugs where 2 will work and then 3 suddenly does not work. Okay, other values that you might want to test, not that it is truly applicable to this program, would be things that will cross the sign limit. In other words, 128. Okay, because 128 represented only as an 8-bit number is going to have the most significant bit set. So when you use 128 to test this code, you are double checking to make sure that you're using the correct flag to branch on this line over here. Because if you use the wrong branch, there's a chance that it will look at 128 as negative 128, and then 42 is returned instead of 45. The correct implementation is to return 45, because 128 is not less than 2. But if somebody uses the wrong flag, then the program can mistakenly interpret 1 followed by 7 zeros as being less than 2. So I'm not going to spell out, which flag is the wrong one to use and which one is the correct one to use, because you probably should understand that part, by this time. Okay, but I'm just pointing out, if you test it using f of 128 and it returns 42, that means the flag used for the conditional statement is not correct. Okay, so these are the boundary cases. Okay, so let's just say the program is working beautifully, when you just have, okay, let me turn on line numbers here. When line 6 looks like this, everything is working perfectly. Okay, so if I were you, I would save a copy of that program, because it means that you have at least gotten the conditional statements done correctly, and also basically you can separate the cases correctly as well. There's a then case that returns a then value, which is 42 in this case, and there's an else value, which is 45 in this case, and your program can differentiate between those two correctly at this point. Okay, so I would save the program, or if you know how to use get, you can go ahead and use revision control, which is a much better way of just saving the file under a different name. But that part is entirely up to you. You are encouraged to use revision control, but it's not required. Okay, so let's say this part is working. So if this is working, then we can start to make the program a little bit closer to what you need it to be. Okay, so we'll just go ahead and say, we'll go ahead and return n when n is less than 2, and with the other one, we'll keep 45, okay? Or you can say 45 plus n or something else, okay? But 45 is fine, because this way we are just checking, do we know how to return the parameter itself, okay? Chances are you probably will be successful in this case, because after all, you need to get to n for the comparison. Okay, so if you can get to n for the comparison, you're most likely going to be able to get to n as a return value. Okay, so that should not be a big deal. The only big deal is, did you copy the value of n into register A? Because register A is the register to return a value. And yes, I just answered one of the questions in the lab for today. Yes, I remember the question. Okay, so if this part is working, okay, then you can go ahead and make it more complicated. And when I say make it more complicated, let's not make it very, very complicated. All we want to do is to make it to do one single recursive call. Okay, so if n is greater than or equal to 2, it would just call f, and then whatever f of n minus 1 is returning, we'll return it too. But then we have a question of, well, if f is like this, what is the return value of f of 128? Or, don't try 128 because you're going to run out of stack space. So 3, 4, those would be much more reasonable values to use. So if you say f of 3, and the logic of f is actually the same, the way it's described on line 8, what do you think x as a local variable of main going to get in this case? Okay, so let's try to figure that out, right? So 3, okay, I'm just going to use my mouse pointer here to help us track the logic. So 3 is passed as n, 3 is less than 2 is false, then we call the subroutine recursively. So 3 minus 1 is 2, n is now 2, 2 is less than 2 is false, then it goes to call f of n minus 1 again. So 2 is n is 2 at this point, n minus 1 is 1, so n is 1 over here in the third recursive call. 1 is less than 2 is actually true, so it's going to return a 1 for f of 1. Then that value gets returned to the invocation to deal with f of 2. But f of 2 doesn't bother to do anything with the return value. It just returns the return value of f of 1 as its own return value. So 1 is returned again, okay, from f of 2 back to f of 3. But f of 3 is also stuck at this part here, which is the else value of the ternary expression. So f of 3 will just take the return value of f of 2 and return that as its own return value back to main. So by the time we get back to main, f of 3 is going to have a return value of 1, and 1 should be what is stored in x. Okay, so this is how we kind of incrementally test the program, okay, to make sure that if I make this program like this with a single point of recursion, at least I can double check and verify that the program is working with a single point of recursion. Okay, if you think, okay, this is way too easy, I don't want to do it this way, you can go ahead and change this just slightly. And instead of just returning f of n minus 1, it is returning f of n minus 1 times 2, in which case it's really doubling for every invocation, which means it is approximately doing the same thing as 2 to the power of n. Now I say approximately because when n equals to 0, it's just going to return 0, which is not 2 to the power of 0. So it will work for all cases of n other than when n equals to 0. Okay, so we got a few questions down here. What makes it easy to find where things went wrong? Okay, that's a good question. I will address that. And then the second one is, does this mean we have to use the overflow flag comparison too? I'm not sure about why we want to use the overflow flag by itself. The overflow flag by itself is only useful when you want to detect that you're trying to store, or the result of a computation is out of range. Okay, that's the only time when overflow is really useful on its own. Okay. All right. So getting back to what makes it easy to find out where things went wrong. Okay. So let's try to answer the question. The trace analyzer, I think, is a very useful tool because the reason that why I said that, okay, in case you guys have not you guys have not watched the video, so let me just kind of point out here. I'm going to move the Discord window over, okay, and then go to the pinned messages. So this one and this one here, okay, the last two videos from the pinned messages of exam 2, those are the solutions of questions 1, 2, and 3. But if you watch my answer to question number 1, you would notice that I made a mistake. Okay, I did not actually implement the program correctly the first time either. And it is the use of the trace analyzer that allowed me to pinpoint what the problem was and how to fix it. So getting back to Nick's question of what makes it easier to find where things went wrong, I would say the trace analyzer is probably one of the most useful tool for that, because using the trace analyzer you can figure out what is happening on the stack. What are you pushing on the stack? Okay, where did you go back to the subroutine? Did you go back to the correct place in the caller? Because if the stack pointer is not balanced, or then it's going to use the wrong byte on the stack as a return address, which means it's going to go to a place where, hey, we are supposed to go back to here, but it did not. Okay, so that is how we can debug a program like this when it is not behaving. But recursion really should not be attempted until we got the non-recursive variation done first. Okay, so line 6, which is now commented out, is the first thing I'm going to try. Okay, it's not too complex. It has a if-then-else structure to it, but other than that, it is relatively easy to interpret. Okay. Once you can get that to work on line 6, then we move on to line 7, and then we move on to line 8. If line 8 is working correctly, in other words, if you say f of 3, it returns 8. If you say f of 2, it returns 4, and so on. Then we can finally go to the place where we have a double recursion. Okay, so the double recursion is f of n minus 2 as the second call. Okay, so the technique to do this has been discussed already, where you have to return the sum of the return values of two separate calls. Okay, so that has been discussed already in the past. It may or may not be a recursive program that did that. I believe it was 5 and 7, and the call is supposed to return a value of 12. Okay, let me just kind of see if I can refresh your memory here. So uint underscore 5. So 5 just returns a constant of 5. Okay. and then we have 12. Okay, I'm hoping you guys still remember this program because I really remember that we talked about this. Okay, so this is returning the return value of calling 5, and the return value of adding to the return value of 7. So if you cannot remember that we went through this exercise, go back to the recordings of past lectures and go through that, okay? Because you will need that technique again in this program. All right, so let's see. No questions up to this point. I'm just checking the text channel. So I'm going to give you guys a few seconds to see if you guys can come up with a question at this point. Okay, no questions. All right, excellent. All right, so we are gonna stop the discussion of the lab, which is your homework assignment. You got a week to work on this. Even though you are allowed to collaborate with other people when you're working on the homework assignment, and Discord makes it kind of easier because you can locate other people and then you can direct message or even form your private group, to have a group chat, when you're working on your homework assignment. It's permitted. It's okay. Nothing wrong with that, okay? But I think it's really important for each person to try to work on this as much as possible individually. At least spend a few days on this before starting to work in a collaborative, method, because otherwise, the learner experience is different. Okay, that's all I can say. Okay, because each group has a different dynamic. So in some groups, it works really well because everybody contributes, and then in some other groups, one person is doing all the heavy lifting, and then everybody else is just asking, "How do we do this? How do we do that? My program is not working. What should I do next?" Okay, so um, that's it's just a recommendation. Okay, try to hold off collaboration until much later. Okay. All right. So I'm gonna stop. I will stop talking about the program that you need to implement for your lab, and then we are moving on to the concept of structures. Are we doing okay so far? Okay. Are there any questions regarding the homework assignment, regarding the lab? No questions about the lab? Okay, all right. So let's move on and talk about structures, which is kind of fun. Okay. For those of you who have taken CISP 430, you have already encountered the use of classes or structures in order to implement complex data structures like trees, linked lists, and stuff like that. Okay, so we're going to experiment with some code like that in this class. Okay, and before somebody is starting to complain and go like, but I have not taken that class, it is not fair. Well, I'm going to give you the code. Okay, so it's not so much that you have to come up with the code to deal with linked lists or traversing a tree. Okay, the code is given to you. It is a question of how to translate that code into assembly, which really should only require the knowledge of C and C++. Okay, and well, CISP 430 is not a prereq to this class. Only CISP 360 is a prereq to this class. So Thomas is correct that it is a prerequisite, but only 360 is a prereq to 310 and not 430. Okay. So let's go ahead and take a look at some code that requires structures. And we'll go ahead and say, well, let's take a look at a list. Okay, so the first thing we do is to define a structure. Okay, and I'm going to pound include stdint standard integer.h, just because this way I have complete control over the size of things. Okay, and then we have a structure, and typically when you have a linked list or a tree, each item in the data structure is typically just called a node. Okay, it's just a thing. Okay, except technically speaking it is called a node and not a thing. Okay, so a thing typically in this case has its own value, So u in underscore u in 8 underscore t, that's the value that we are storing with that particular with the structure. And then very typically it has something that looks like this. Okay, if it is a linked list, it's usually called next, and pointed to the next node. If it is a tree, then you end up with two or more pointers to the left hand side, to the right hand side, or to various places. Or you might sometimes have an array of pointers to nodes. Okay, but I don't want to complicate things at this point, so I'll just go ahead and say that yeah, we only got one pointer to another node. Okay. So if you have taken C and C++, in CISP 360, and you recognize what a structure is, you know what is how we define a member inside the structure, but you might find this definition a little bit strange because we are okay. Let me turn on line numbers so I can refer to the lines. So line 6 looks really kind of suspicious. It's like, well, we are inside the definition of a node, and can we really use struct node in a definition like that? Okay, so that looks confusing, but it is really not that confusing. So let me just kind of pause because I thought somebody wanted to ask a question. So I'll just kind of pause for a few seconds for that person to ask their question. Nobody? All right. Does anyone have any questions? All right. So if nobody has a question, then let me continue to talk about what this is really doing. What is line 6 doing? Okay, line 6 is not making a member a struct node. Okay, that is not what pnext is about. Pnext is not a struct node. It is a pointer to a struct node. All pointers are really the same. Okay, so when you look at C and C++, okay, this is a void pointer. Okay, ptr, struct node. This is a pointer to a node. U in 8 underscore t. We'll call this p to some kind of unsigned integer, and it is a pointer. And let's make it just make one more. Okay, just to so that we understand what a pointer is. Okay. So we'll make one more, and I'm trying to think about what kind of a pointer it should be. Let's make it a pointer to a pointer. Okay, so it's a void pptr. Okay, it's a pointer to a pointer. So when you look at line 9 all the way to line 12, okay, you go like all of these are different pointers. They are all kind of different. Because ptr is a void pointer, we are not supposed to dereference it because you cannot dereference something of a type void. Okay, pnode is pointing to a structure, puint is pointing to an unsigned integer, and then pptr is pointing to a void pointer itself. Okay, so pptr can be dereferenced because when you dereference pptr, it is the type of the dereferenced expression is a void pointer itself, so it can be dereferenced with on line 12. But guess what? In assembly, they're all the same. Okay, because all we are saying is, okay, when we look at any pointer, all we are saying is it is storing an address. Okay, so ptr is storing an address. An address of what? I don't know because void doesn't tell me what type it is. Pnode is storing an address. An address to what? Oh, according to the C code, it is the address of the beginning of a struct node. PUINT is an address. Okay, it stores an address. An address of what? Is an address of an unsigned 8-bit integer. PPTR, okay, is storing an address. What is an address of what? It's an address of another address. Okay, what could you return with void? I'm not really sure about what the question is asking. So if you have a void function, you cannot return a value. And if you try to dereference a void pointer, the compiler will complain because there's no such. The whole point of void is there's no such type. Okay, so you cannot dereference a void pointer and say, oh, here's the value of where the pointer is pointing to, because a void pointer is only useful to be casted into a different pointer when you dereference it. So is that does that answer the question? Does it answer Eugene's question? Okay, cool. All right. So apparently, all of these things are different in C, but in assembly there is no such thing as type, which means when you use, whether something is used as a pointer, it all boils down to, are we going to where that thing is pointing to and then access the value that it is pointing to. So there's no actual pointers, whatsoever, or there's no type associated with pointers in C and in assembly code. In C and C++ there is, but in assembly code there is no difference between all of these pointers because nothing is typed in assembly language programming. Okay? So that means, okay, in this case, P next is really just a pointer. Okay? You can basically say, okay, let me get down to here. Okay? If you are getting a little confused, or if you're not quite accepting that we can use struct node pointer as P next, think of it as a void pointer. Okay, just think of it as a void pointer. Okay, fine. Okay, so now the question is, what do we use that pointer for? Okay, so when you have a linked list, okay, and well, let's just say that we want to initialize a linked list. Okay, so this is the code that I'm going to write, and we'll translate it into assembly in just a little bit. Okay, let's see, how should I do this? Okay, I know exactly what to do. Okay, so let's go ahead and change this back because I do want this code to compile. Okay, because if it does compile, at least we got the C code to play with. So what I'll do is I'm going to have some global variables. This is one of very few times when I make I make use of global variables. So I would say struct node node 1, okay, equals to, and then using braces. Now I can specify what the value is. We'll just pick a random value 5 over here, and now I also want to specify what is P next of node 1. Okay. So because I don't have any other struct nodes defined at this point, I'm just going to use a null pointer in this case, which is basically a 0. Okay, when you use the word null, N-U-L-L, all in uppercase, it really just boils down to 0. Okay, and you might say, but the compiler is going to bark at this. It's going to choke on this one because 0 is an integer and P next is supposed to be a pointer to a struct node. Okay. My bad, I forgot to specify node over here. And there's a question, will declaring it as a struct node pointer help allocate the memory on the stack? The answer is no, because all pointers have the same size. Okay, a pointer to void, a pointer to an unsigned 8-bit integer, a pointer to a struct node, they are all the same size on any architecture. Okay, so within the same architecture, all pointers have the same size. For instance, if I compile this program using a 64-bit compiler, then all pointers have 64-bit. They're all 64-bit wide. A void pointer is 64-bit wide. An integer pointer is 64-bit wide. A struct pointer is also 64-bit wide. Why? Because the address space is really 2 to the power of 64. So in order to specify a location in the entire memory space, you need 64 bits. The architecture that I use, okay, the toy processor architecture, only has a memory space of 256 bytes. So all pointers in that particular architecture, they're all just one byte, okay, because you just need 1 byte to locate one location in 256. All right, so let me continue with this. Okay, so we have node 2. And I want the value of node 2 to be, no, let's say 23. But now that node 1 is already defined, P next, which is the address of a node or pointer to a node, now I can refer to the address of node 1. Okay, and just to make it slightly more interesting. We have a node 3, and this time we have, let's use 42 again. Okay, it's really cool. So this is the address of node 2, like so. Okay. So do we have any questions about line 9, 11, and 13? What they are doing? Okay, we have initialized global variables, and each one is of the type struct node. So do we have any questions about those 3 lines? Because this is kind of what I'm trying to demonstrate. What is a member when it is a pointer to the same type that we are trying to define. On line 6 of the struct node definition. Angel has a question. Okay. Yes, I still wasn't understanding what a pointer is being used for. Okay, so let's go ahead and just compile this program, and then we'll use the debugger to help us understand what this thing is trying to do. Okay, so we'll say return 0. I'm not sure whether you. Okay, somebody is trying to say something. Go ahead. All right. Okay. All right. So I'm not sure whether this program will. Okay. So I'm not really sure whether this program will compile. Well, whether I can track down the global variables or not. Um, but then we'll give it a try. Okay. It's okay, Jacob. We all forget to do something at some point, and me particularly forgetting more things usually. Okay. So it doesn't like that because of the previous line probably. So line 9. Okay. Yep. Okay. This is a really nuisance when it comes to the syntax between the differences between C and C++. In C++, if you have a class definition, you do not need a semicolon after the close brace for the class definition. But when you're using regular C, you need a semicolon after the brace after a structure definition. A structure really is basically the same thing as a class where all the members are public, but in terms of syntax, there's this kind of minor thing that is not the same when it comes to how C and C++ compile. Basically the same idea, same concept. All right, so now everything is good. We say GDB list, okay, and we can probably, yeah, we have to run the program first, because if you don't run the program, the global variables are not even initialized. Okay, they're not even there yet. So we have to put a breakpoint on line 18. Okay, run the program. Now we can play with it. Okay, I can say print node 1, and it will print the entire structure. Okay, we know that GDB can do this because of the homework assignment, for the floating point numbers. Remember, with the floating point numbers, I give you a structure. I give you a pointer to a structure to get into the subroutine, and to find out, what is the mantissa or the exponent of 2 or the exponent of 10. You just have to dereference the pointer to get to the structure, and we can print out the entire structure, in that particular exercise. Okay. So, okay, nothing too fancy about node 1, okay, because node 1, after all, really is just initialized to have a value of 5 and a null pointer. Okay, so the null pointer is fine, it's just 0. Okay, so what about node 2? So when you look at node 2, things gets a little bit more interesting. Okay, value is not interesting at all. Okay, it's 23 because that's how we initialize the first member of node 2. But when you look at the second member, which is p next, okay, it gives you something that looks like this, which is an address in memory space. But at the same time, GDB is so smart that it recognizes this and go like, hey, I know this, I recognize this. This is the address of node 1. Okay, so if you follow p next of node 2, you will find node 1. Okay, so not really surprisingly anymore, because this is basically the same thing. When you look at node 3, Okay, the value is 42. Forget about the asterisk. Okay, the asterisk is really just GDB being smart and go like, hey, this is an 8-bit wide integer. I will even give you the ASCII interpretation of that particular number. That's what the asterisk is, because 42 in decimal is the ASCII code of asterisk in ASCII. Okay, so forget about that, it's not important. But P next is important, because P next of node 3, okay, is the address of node 2. But when you look at P next of node 2, it is the address of node 1. And then finally, when you get to node 1, the P next is a null pointer, because that's how we indicate this is the end of a linked list. Okay? This is how we make a linked list in CISP 430. So Angel has a question. So the pointer is used to link each structure together in a chain. Yes, that is exactly what it is doing. Okay, it is just it, each node has a pointer that can help that node to find who is the next one. Okay, is that okay? Do we have any questions at this point? Okay, because even though pointers and structures are concepts already covered in CISP 360, the combination of these concepts may be new to some people in this class. No questions? Cool. Okay. All right. So without any questions, we got to go back to this program and we'll see, can we add up all the values of the different nodes in this particular chain. Okay, so that's, we just want to add up 42, 23, and 5, and then we just say, okay, we stop here because that's the last link of the chain. Okay, so let's go ahead and write some code to do this. So we got struct node. I'll just call this PTR, which is a pointer to a struct node. And then we'll initialize PTR to be the address of node 3. And then we say, as long as PTR is not null, okay, I'm using a very lazy syntax here, we'll go ahead and add up the values. So we have uint 8 underscore t as the sum, and then we initialize sum to 0. And then for each iteration of the loop, we got two things to do. Sum plus equal to PTR points to the value. Basically, it's the member value of the structure that pointer PTR is pointing to. And then at the same time, we advance the pointer to the next node if there is a next node. Okay, so PTR, the pointer is PTR, the P next member of the structure that PTR is pointing to. Okay, so let's just go ahead and stare at this code here, okay, and see if there are any questions. Okay, if you just focus on line 18 to line 27, do we have any questions? The purpose of this code is to start with node 3, and then for each node that we visit, we add the value of that node to the sum, and then we move on to the next node. So we hop from node 3 to node 2, node 2 to node 1, and then at node 1, PTR will eventually become 0 because the P next member of node 1 is a null pointer. So PTR gets a 0 in the last iteration. So when we get back to line 23, PTR is 0 and it is no longer non-zero, and that's how we are going to get out of the loop. So there's a question: how can assembly recognize PTR and P next relationship the way GDB does? Okay, very good question. So this is basically where I'm heading. Okay, I just want to show the C code first, make sure that everybody understands the C code, then we'll go ahead and write this code in assembly. Okay, so very good, Angel. You're already thinking about the next step, so that is really cool. Okay, so we'll go ahead and compile this code. Okay, and then we'll GDB the code. This time you can actually set up multiple breakpoints. A breakpoint on line 23 can be quite useful, and then a breakpoint on line 29 is going to be quite useful as well. Okay, so we'll run the code, And now we are stopping on line 23. Okay, the first thing is tell me what is PTR. Okay, PTR is 5555 blah blah blah, ending with 50 in hexadecimal. That's really hard for a human to read. But GDB is so smart that it recognizes this and go like, yeah, I actually know what this is. This is the address of node 3. Okay, so on line 23, PTR uh, is is a pointer to node 3. We single step. Okay, so we can, before we perform this statement, we can even ask GDB and say, hey, can you show me the value, member value of the structure that PTR is pointing to? Okay, it's 42. Well, it's not really surprising, right? Because that's exactly how we initialized node 3 as a global variable. Okay, so single step. Now we ask, hey, what is P next? Okay, what is the member P next of the structure that PTR is pointing to? Okay, it is the address of node 2. Okay, not very surprising because when we statically analyzed the C program, that was basically the conclusion. Okay, we already know that. Okay, but when we single step, okay, we're getting back to line 23, but that's after we use member P next of the structure that PTR is pointing to change PTR itself. So at this point, PTR is going to be the address of node 2. Okay, so we have moved from the first link of the chain to the second link of the chain. Okay, so we single step. Okay, if you want to do this, okay, you can print it out. Single step again, and then we look at this again. Okay, now it's going to node 1. Single step again. So now when we look at PTR, it is the address of node 1. This is the last link of the chain. Okay, so we single step, and then one more single step here. Okay, this time PTR is null. Okay, which is the same thing as false. Okay, so we are going to stop the loop at this point. We're going to exit the loop. So when we single step, it is no longer going to the next line. It is going to the return statement at this point. Then we can say, okay, what is the summation of the values of all the nodes that we have visited? Okay, it's 70. So that kind of makes sense, right? It's 42 plus, okay, I cannot remember. 42 plus 23 plus, what was node 1 again? Okay, 5. So adding up to 70 is in fact correct. Okay, so let's try to implement the same thing, but this time in assembly. Okay, and let me just check the time. It's 6:36. We got plenty of time to do this. Okay, so if you guys have any questions, go ahead and ask those questions. Okay, so we'll go ahead and implement this. Okay, but we'll look at the main the C implementation, while at the same time look at the work on the assembly code. Okay. Oh, okay, this doesn't work. That was not my intention. My intention was to do a dash uppercase O. What this would do is kind of cool. It would display side by side the two files. Okay. So in assembly code, remember we don't have a structure, but instead of using structures, we can make use of labels. So we can say node underscore value to be 0 because it is at the beginning of a struct node structure itself. And then we say node underscore p next, okay, to be node underscore value 1 plus. So this 1 in the 1 plus has to do with the size of the member value. It is an unsigned integer, and because we have a byte wide native memory width, so that means we can really just allocate 1 byte for the member value. And I usually also specify the size of a node, okay, because it comes in handy if we need to allocate it on the stack. That is going to be needed. Not so much with this program at this point, because we don't have any struct node that is a local variable that lives on the stack. Okay, so with this particular program, it is not a big concern, but it's always a good idea to use one label to define the size of a structure. Okay, so these lines, okay, these three lines is basically doing this what is equivalent to the structure definition in the C code. So now we can move on to the global variable initialization. So, well, it's not really that difficult, okay, because we just say node 1, okay, this is a label definition, and then we use byte, okay, to specify the first one is 5 and the next byte is a 0. This is how we initialize a structure statically as a global variable in assembly. Okay. Now there are some problems that we have to fix in this code, but we'll talk about that later. So node 2 as a label, okay, is representing the beginning of struct node 2 in the C code. So let me turn on line numbers in the C code, so this way it's easier for me to refer to the C code. So on line 11 of the C code, it is initializing node 2 as a global variable. So we'll go ahead and say byte 23, which is the value, and then the way we specify the address of node 1 is simply to refer to node 1 as a label. Okay. I believe we have seen something like this, early on, in one of the labs for to learn how to use the assembler. Then we got node 3. The value is 42, and then the p next value, or the address, is the address of node 1 or node 2, excuse me. There we go. So this is how we initialize the three struct nodes in assembly code. Okay, we simply use the byte directive to say, here's a byte. Okay, what is it storing? 5. Okay, here's another byte. What is it storing? 0. So this is how we allocate the space and initialize the content of the structures that are global. Okay. Then we got main over here. Wait, hold on a second here. If main is over here, don't we need to tell the processor to jump around the node definitions? Because otherwise it will execute 5 as if it is an opcode. Okay, because it's the first byte of the entire memory space. So the answer is yes. Okay, we don't want to do it like this. This is what I was trying to refer to a little bit earlier. Is the no op is only here because in case we want to trace this code using the trace analyzer, the no op is needed, and then we have a JMPI to jump around the definition of the global variables. So this time, when we get to main, we'll just go ahead and halt, okay? Because all I want to do is to get this code to assemble, and then we'll use the assembler to tell us what is going on, when we run this code. Okay. I'm going off the screen a little bit because I want to learn how to use xclip. Hugh told me how to do it, and it was not working correctly last time, I think. So dash I is to read text into the X selection from standard input or file. Okay, F is filter. I don't think that is needed here. Target, display. The default should be fine. Specify which X selection to use. Options are primary. Okay. Okay, so that should work. Okay. So I'm gonna shout out here. Oh, I have to save the file first. There we go. Oh, okay, I just exited, that particular portion of the editor. So we'll try to do this. Okay, list.ttp.asm. And then we'll paste it back to some place so I can see whether it works or not. Well, let's go ahead and try the assembler. See if that works. And by the way, I found a bug in RC2, so once again, I think it's working. Nope, it did not work. Okay, that was the link to today's lecture. Okay, that did not work. Okay, well, the other way is to just mousepad it and then copy and paste from mousepad. Mousepad list.ttp.asm. Control A, Control C, and then Control V over here. Okay, here we go. So we want to go to the Assemble tab because the Assemble tab, gives us a lot of information because it not only does it show what bytes are allocated, it actually tells us which line is generating which byte at which address. So that makes it, that makes the Assemble tab actually surprisingly useful for, for when we need to debug the program. Okay. So line 1 is just defining a label. Okay, the label is defined to be 0. Line 2 is defining another label. Okay, the label definitions are all in the symbol table. I can show you that later. So the first line that actually generates any kind of bytes in RAM is line 5. Okay, no op, will generate a single byte, which is 0, 0. We know that because that's just the um, uh, that's the opcode of no op. And then the second instruction, JMPI, is generating 2 bytes because it's an immediate type of opcode. So 40 is JMPI itself, and then main as a label is 09, and we can check that main is defined over here, and it is in fact at location 9, so that's all good. But the main focus here is where is node 1? Node 1 is at location 3, so the address of node 1 is location 3. So at that location, what do we have? Okay, at location 3, we have a value of 5. At location 4, we have a value of 0, which is the null pointer, what we know as p next in the C structure definition. And then when we look at node 2, this gets a little bit more interesting. Node 2 itself is at location 5, which is not surprising, because if node 1 is at location 3 and each node only needs 2 bytes, it kind of makes sense that the next node is going to be at location 5. The byte at that location is 17 in hexadecimal, which is 16 plus 7, which is 23. That's fine because that's the value member of that structure, and that's what we want to initialize that structure, that value to. But when you look at line 14, this is where things get a little bit more interesting because this is supposed to be the address of node 1, and guess what? It really is, because this 03 is an address. It is a pointer. It's a pointer to point to the beginning of node 1, which is at location 03 over here. So, and then when you look at node 3, node 3 has a p next pointing to node 2. So when you look at the byte, the value of the byte at location 08, it is 05, which is the address of node 2. So this is how things are organized in memory when we use structure, when we have initialized structures and it forms a linked list. So do we have any questions at this point? I'm just going to check the text channel and see if we got any questions here. So Angel is typing. So as Angel is typing, I'm going to switch back to the text editor to finish the program because I really want to finish this code tonight so that you can look at the C code and you can look at the assembly code. So we'll go ahead and look at these two codes programmed side by side, and I'm keeping an eye on the text channel. So when Angel is done typing, okay, that's interesting. Bytecode correlates. Byte node correlates to the address of the label, which is also the address of the struct itself. Okay, so what the label is doing, okay, let's go back to the Assemble tab here. So node 1 as a label really doesn't care what is at that location. Okay, all it does is to say, I am the symbolic name of the address at this point, which is location 3. That's all node 1 is remembering, is to say, I am the symbolic name of the current address in the assembly process, which is location 3. Okay, now is location 3 code that we can run, or is it just a byte, which is turns out to be a member of a structure, or what is it? Node 1 does not care. Okay, so the next byte 5 is what we use to initialize that location to a value of 5 because the value member of node 1 is supposed to be 5. Okay, yes, yes. A label is really just a symbolic name, and when you do not have any expression to the right hand side of the colon, a label becomes just the symbolic name of an address. Okay. All right, so let's switch back to here and let's go ahead and try to finish this code. So going back to the assembly side, okay. So I'm going to use the same trick, the same usual standard. Okay, main has no return address, but it has a PTR as a local variable. So we'll go ahead and define that one first. Okay, so it's a 0. Okay, because the stack pointer will be pointing to main pointer. No, that is not true because we have another local variable down here. So we'll okay. This is somewhat new to us. Okay, so where do we find some? It's going to be 1 byte below main pointer, so it's going to be so sum is supposed to be 0, and then PTR is 1 byte above that. Okay, because it is allocated first, and then sum is allocated later. So this is main sum 1 plus. The assembler can resolve references to labels forward or backwards, so this is not a problem. So we now need to implement PTR equals the address of node 3. Okay, so the address of node 3 is really just the label node 3 itself. So LDIA node 3 is going to get that task done. Okay, so A is now the address of node 3 in C code. So that's the entire right hand side of that line. But we need to store into a local variable PTR. Okay, so that's something that we have to do next. And I totally forgot about a few things that are kind of important. The first one is to initialize the stack pointer. So subdd will initialize the stack pointer to 0. Okay, it's really doing the same thing as LDID0, except it is slightly more efficient because it's just a 1 byte instruction instead of a 2 byte instruction. And then the second thing we have to do is to decrement d twice because we need to allocate storage for the local variables. PTR is only 1 byte, and then sum is also just 1 byte. So with that, now we can actually figure out where we're supposed to store register A to. So we use the usual trick, LDI B this time because A is already in use. So B, and then we say main underscore PTR, add BD, and then STBA. So now we have accomplished PTR equals to the address of node 3. And then next we have to initialize sum to 0, LDIA with 0. But wait, Tack, you just mentioned a trick to 0 a register using the sub instruction. So yes, so sub AA is going to clear register A. Okay, A is now 0. And then we store it to sum. Okay, so kind of the same deal as before. LDIB main sum, add BD, STBA. Okay, so this will initialize local variable sum to 0. So now we got a loop. Okay, so every time you have a loop, you have to define certain labels kind of like right away. So we have while one begin, while one end, and then at the right before the end we have to jump back to while one begin. So I'm writing the loop like this because I know these are needed. Okay, and we also know right before the halt we have to increment d twice to deallocate the local variables. So that needs to be done too. So now we can focus on the condition of the loop. We are looking at PTR to see whether it is 0 or not. If it is 0, we get out of the loop. If it is non-zero, we stay in the loop. That's basically what we need to do. So we say LDIB main PTR, add BD. So the B is now the address of the PTR variable. And then we just need to dereference it once. Okay, LDBB. Okay, so at this point, it is important to know that register B is not what pointer is pointing to. It really is just the pointer itself. Okay, because before this line, at this point, B is the address of PTR. So when you dereference it, you're really just getting the pointer, not what the pointer is pointing to. Okay, and then once we get B, we can now test it, right? So we need to see if it is 0 or not, but you don't need to use the CMP instruction. We can use the AND instruction. This is a trick that we have learned a long time ago, a few weeks ago. So we can AND register B with register B itself, which is basically, it's testing register B. And if the Z flag is set, it means register B is a 0, which coincidentally and conveniently is when we need to get out of the loop. So we can say, okay, let's go to while one AND at this point. So this is now the body of the loop. Okay, the portion where the cursor is the body of the loop. We need to retrieve the value of the structure the PTR is pointing to and then add that to the sum variable. Okay, I know it is a mouthful, okay, but that's basically what we need to do. Okay, so it looks like what we need to do is to get to pointer first. Okay, the value itself, okay, value itself is really just the name of a member, so it is not that useful until we know where the structure is. Okay, because if you want to access a member of a structure, you first have to know where the structure is. Okay, so we need to access pointer first to find out where the structure is located. So to get the pointer is to use the very same trick that we have used already. If you say that, oh, but we got pointer in register B already, you're absolutely right. So let's make use of that. Okay, so B is already PTR, the pointer, which is the beginning of a structure. Okay, so if I know where the beginning of the structure is, then I can now say, how do I figure out the address of a member of that structure? So the way to do that, okay, we'll use register A in this case, is to load the offset from the beginning of the structure to the member that we want to access. That turns out to be node underscore value as a label. Okay, and then we add AB in this case. So we are adding the address of the structure to the offset from the beginning of the structure to a particular member. So this way we can get to the address of a particular member value in this case. So if I were to comment this, A is now the address of the value member of the structure that is pointed to by PTR. Okay? But we don't want the address, we actually just want the value of that. So we can use a LDAA, so that A is now actually the value of the member value of the structure that PTR is pointing to. So now we can just try to add it to sum. Okay, so we use LDIC. I don't want to reuse B because B is still useful for the next statement, so I'm using register C in this case. It's sum, so this is main underscore sum, which is an offset again, but this is not an offset related to any structure. It is an offset to find a local variable in this case. So we have to add CD, so that C is now the address of sum. And we don't want to use LD to dereference it. Well, actually we do. So we want to use LD to dereference it first, so that C, let's see, am I running out of registers? I need A, I want to keep B, and now I want to keep C too. The reason why I want to keep C, being the address of sum is because I need to store it back into the local variable. So, so I'm kind of out of registers, at this point. If I'm out of registers, I can always use a trick and push a register on the stack and then retrieve it later on. So that's what I'll do so that I can reuse a variable, a register that is going to be destroyed in this case. Register A is needed right away, okay? Because register A is the right hand side of the assignment, so we're gonna need it right away. Register C is also needed right away because it is the left hand side, or the address of the left hand side of the sum plus equal expression. So the only variable or the only register I can kind of spare by pushing it on the stack is register B. Okay, so I would just say push register B on the stack, and to do that is a decrement D stdb. Okay, that's pushing register B on the stack so that we can retrieve it later. So now I can use it for the time being. Okay, so I can say ldb C. So the register B is the value of sum at this point. We want to add to register B register A, so that now register B is sum plus PTR points to value. Once we have the sum, we want to store it back to where register C is pointing to, because register C is still the address of sum. So now we do a stcb, so that sum is now actually storing the value of sum plus pointer points to value. So at this point, register B can now be retrieved because I'm completely done with the sum plus equal to expression. So I can now pop whatever the stack pointer is pointing to back into register B. So that's a LD BD and then an increment D. So now we can continue with the next line. Okay, B is once again pointing to, or did I? Yes, so B is still pointer at this point. Okay, so B is pointer, and this time we want to find the member P next. Okay, and get that and then put it back into pointer. So we'll go ahead and use the same trick as last time. So we'll use LDI A node underscore P next. So A is just an offset. Okay, register A is an offset from the beginning of a structure to the member P next. Okay, B on the other hand is the address of the beginning of a structure. So if I add those two, I will get to the address of the member P next of the structure that PTR is pointing to. So if I say add A B, then A is now the address of the P next member of the structure that PTR is pointing to. So I know this is a really long mouthful, okay, and it's really kind of abstract when it's only in text. So I strongly recommend people to look at this code and draw a picture, okay, of what each register is pointing to, if it is something that can be dereferenced, and then for each statement, for each instruction, kind of move that pointer around so that you understand what that pointer is pointing to at which instruction. Okay. So now A is the address, but I don't want the address. I want the actual value of P next. So we have a LDAA. It's okay to destroy register A, which is a useless address at this point. So now A is PTR point to next. Okay. And we want to store this to PTR. Okay. And the cool thing is register B is PTR, but it's not the address of PTR. So we have to recompute the address of PTR because that's what we need to store into the local variable PTR. Okay. Let me just kind of pause here. Is everybody still kind of following what is being done? Cool. All right. So B is main PTR, which is the offset. And then we have add BD so that it becomes the actual address of PTR. And this is where we can do a store from register A so that we are moving the pointer itself ahead to the next link of the chain. And that should complete the body of the loop. Okay. should be the code that we need. Okay, so we'll go ahead and give it a try. Copy and paste it into the assembler. Uh-oh. It doesn't like it. Or it's just taking some time. No. Ah, okay, much better. So we get to RAM file. Okay, so it's all good. File, download as CSV. And we'll save it as list.csv. And then we'll run it using a command line. And it's going to be 2024. And that's for question number 1. So we want to change the CSV, which is the RAM content, to the program that we want to debug at this point. All right. So now we go to the trace analyzer and go to sheet 1. Do the import. It's list.csv. Replace the current sheet, tab, and say no here. Oh, okay. My mistake. I made this mistake several times already. I imported the wrong file. It's supposed to be log.tsv. There we go. Alright, so import data. And on my computer, it takes about 6 seconds or so before the analysis tab is presentable, which is a lot faster than before. Cool. All right. So we'll go look up the code, and so I'm trying to be optimistic and say maybe this code really works. And then we go all the way down here, and we want to find out what we actually stored into local variable sum. Okay, and we want to find out where sum is. Okay, so we got 2 local variables. The first one is PTR. That is the one that is at location FF. So FE is the address of sum. So we want to know what is the last value that we store in location FE. So the last value we store in location FE is 46, or 46 in hexadecimal. 46 in hexadecimal is 4 times 16 plus 6. 4 times 16 is 64. 64 plus 6 is 70. So we got our 70 back. So as far as I know, this code is working. Okay. But PTR is also supposed to be null, and PTR is at location FF. So we want to look at the last update to location FF. It is in fact 0. So this is where we store the null pointer into PTR, which is our local variable, and that will lead us out of the loop, and that's why we got out. And we balance the stack by incrementing the stack pointer twice to deallocate the local variables. So everything works correctly in this program. I basically got it working the first time, which kind of surprises me. So Do we have any questions at this point? I know I'm running over time again, but in case there are any questions, I'm more than happy to kind of address those questions as they come up. No questions? All right. Well, I'm going to ask a question then. Is anyone interested in having me to post the code that I wrote tonight, especially the assembly code? You got 2 seconds to
Yes,
reply.
please. I would
Okay.
like
I was trying to say, yep, you got 2 seconds to reply. Okay, yes. Okay, so I'll go ahead and, well, we can attach it. So I'm just going to attach it in Discord. Is that okay?
You gonna pin it to the top? That'd be fine.
Yeah. Okay, so we'll do it this way. I'll just put the TTP ASM file, the list program in assembly, upload, and I will also post the C code because it's good to be able to look at both of them because they are related. So we want to look at list dot C. Where's that list dot C program? Did I move it somewhere else? Hmm. I cannot remember how I named that file. It is list.c. Okay, it's under the temp folder. Maybe that's why. Okay, I'm talking to myself because I'm trying to find list.c. No, it's not there. Why is it not there? Hmm. Okay, let me try one more time. There we go. Found it this time. Don't know what happened last time. So this is the C code of the list program. Upload. And I'll go ahead and pin both of these messages. All right. Okay. So it's all done. So when you get to these programs, okay, you can go ahead and download it. TTPSM is relatively documented, um, but in order to really understand the concepts, it's not just enough to look at the code. Okay, as you go through the code, it is a good idea to draw a picture so that you can see. Oh, okay. Register B is pointing to the beginning of a structure, and register A is an offset from the beginning of the structure to a member of that structure. So when you add those two registers, then you have the address of a member of a structure that is pointed to by a pointer to begin with. Okay, so so going slow, using pictures to kind of annotate, what is going on, with the program is going to be very helpful. Now, I can track most of this stuff without drawing a picture, just because I have a lot of experience doing this. But if this is the first time that you encounter programs like this, it really is helpful to go through it line by line. Okay. The other resource to help you understand, this particular program is to look at the trace analyzer. Okay, is to combine the comments in the assembly source code with what we can observe in the trace analyzer, because the trace analyzer will quite clearly display which register at which point has the address of which member of which structure. Okay, so everything um, is presented in the trace analyzer in that fashion. So when you combine the source code, a picture that you draw, okay, to help you understand which register is pointing where, and also the trace analyzer, which is a great tool to confirm that your understanding is correct. That combining all of those activities will really help you understand the topic of today. I understand this is a lot of stuff to sink in, and the way to dig through all this stuff is to follow the program and then add your own explanation and annotation into the code, into the trace, and so on. So I hope this is all okay. Okay, because on Thursday, what we'll do is we'll go ahead and kind of look into a combination of what we talked about tonight, which is accessing a member of a structure, and we can combine that with recursion. Yes, I know it sounds like a big, huge headache, right? But those two concepts are what we call orthogonal. Okay, they don't interfere with each other, so they can be combined with. They can be combined, to do really, really powerful stuff. Okay, so that's what we'll be talking about on Thursday. Is start to combine recursive stuff with structures. So, do we have any other questions before I sign off from live streaming? No questions. Okay. I got a private message. Let me see if that is related to class. And nope, not related to this class. It is related to my 440 class, but not this one. So I will address that later. Okay. So there are no questions. All right. So if there are no questions, I am going to